for which we are asked to get an upper limit for the ground state energy. Okay, and mic please off. Then what we will do? We have to make guess. What we will do? We will start with a wave function, say that is of Gaussian type, a to the power minus alpha x square, a wave function that has of the form x square plus b square, a wave function of the form b to the power minus ax, a wave function of the form that is of the type c to power minus x by a by x by a, or dot dot dot. Okay, that means I have many trial wave functions available with me, and I will try one by one with each of the wave function, and then we try to get the ground state energy. I have started with this and I have obtained the ground state energy. Now I will go back to the experiment and we'll see that whether my result matches with the experimental result or not. If it matches, or if it is a very close number, then we will say that okay, that wave function for the given system is Gaussian type, and if there is a small deviation of say 1%, 2%, 5%, then we will tune this parameter to get the final result. But if it does not, then we will try with this wave function. If it does not, then it will try with this wave function. If that does not help, then we will try with this wave function, and we will keep on doing it. And then you will say that, sir, this is a donkey's work. This is not physics. You have got so many wave functions, and you are telling me to try this one or this one or this one or this one, and we know that the real life problem is not very simple, and therefore it is not possible to obtain the solution for the upper limit of the ground state energy. Okay, and that is why there is a very limited problem to which we can apply variational principle, and most of the time the problems which we are supposed to discuss in the class are those problems for which we have already the solution from the time independent Schrodinger equation, which matches with the experimental results, like hydrogen atom problem or harmonic oscillator problem, or a few more problems. Okay, therefore the important point is that in general it is really very difficult to make guess. Otherwise, if it had been easy, then there was no point in solving time independent Schrodinger equation and all that. But the important point is that we can apply, and that is what we are supposed to do in today's class, not today, but tomorrow's and day after tomorrow's class, to use a few problems to obtain the upper limit for the ground state energy of the given system. And the given system that I am telling you would be a harmonic oscillator problem, hydrogen atom problem, or one or two more problems which are given in the Griffiths exercise. Okay. Now the important point is, how do we proceed? Now, first of all, the important thing is that whatever wave function we are writing, first of all, we have to ensure that that wave function has to be properly normalized. Okay, therefore the first important point is, before proceeding ahead before proceeding ahead to get the energy eigenvalue for the ground state, it is essential, it is a must to normalize the wave function, and that means this psi must be equal to 1. This is the most important step of variational principle, that you have to first normalize the wave function. Okay, and then you have to obtain the expectation value of h. But for example, say your wave function psi is the wave function for the excited state, then what will happen? The expectation value of h will exceed the ground state energy. Okay, and that means if you have the wave function psi, then you can express that psi in terms of the complete set of eigenfunctions which span that Hilbert space. Therefore, any psi that you talk about should be able to be explained in terms of the eigenfunctions which spans the Hilbert space, such that your h psi n is equal to En psi n. That means this we have done it in the class, but I am repeating it. If we have expectation value of h, first we have ensured that our wave function is normalized. That is why I am not writing this in the denominator, otherwise this has to be there. Psi h psi, this will be equal to some am, say psi m or phi m, whatever we call. This psi m is different from this psi h, operator an psi, and then m and n summation sign outside. Am, when we will take out from the bra, this will become am star, this will remain an, this will be psi m h psi m. And what is psi m h will operate on psi n? This will give us En psi n. Therefore, this is Mn Am star An En psi m psi m. Now we know that these eigenfunctions, these are orthogonal and properly normalized. Therefore, this we replaced it by delta Mn, and when we replace it by delta Mn, then that means this is going to contribute only when Am is equal to An, and that means this is equal to An mod square En, and expectation value of h is going to give you what it is going to give you the energy E, okay, and that means that your ground state energy that you are talking about, okay, that ground state energy or the expectation value of H, this will always be greater than the ground state energy of the system times an square. And since on the right hand we have seen that summation of all an square, here also I should write summation of all an square, this we have done in the class, this is 1, therefore this will be equal to E ground state. And that is why we say that the variational principle gives us a method to find out the energy, okay, the ground state energy of a given system or the one of the excited states by starting with a wave function, and first of all we normalize this wave function and then we try to obtain the observables corresponding to that wave function. For example, if I have the wave function which is properly normalized, say that is a times minus bx square, which is nothing but a Gaussian wave function. The Gaussian wave function looks like something like this, a Gaussian symmetric around the origin, a Gaussian wave function, okay, a to the power minus bx square. Then first what we have to do, we have to normalize it, and then once we normalize it, we start to get the observables. But at the same time, the important point here is this A and B, they are unknown quantities. A will determine when we will normalize the wave function, and B will determine when we will say that for the ground state, any variation in the expectation value of H, that means any variation in the expectation value of H for the ground state, this should be equal to 0. This will be the condition where we will determine B, and this will be the condition where we will determine A. Therefore, A and B, these two unknown quantities, will be determined by putting this condition and this condition. But before that, once we have psi, we normalize it. Then, for example, if we are asked to calculate kinetic energy, then kinetic energy is P square by twice m, and that is, say, minus H square by twice m, in general del square, but for one-dimensional problem we may write it as minus H square by twice m d square by dx square. And that means physically what is this? This will be minus infinity to plus infinity psi star minus H square by twice m d square psi by dx square dx. This will give us the kinetic energy of the system. If we are asked to calculate the potential energy, expectation value for the potential energy, depending upon the problem. If you are talking about the hydrogen atom problem, the potential energy will be 1 by 4 pi epsilon naught E square by R, or with a negative sign. Or if you are talking about harmonic oscillator problem, then that will be half m omega square x square. Therefore, if it is harmonic oscillator problem, then this will be half m omega square x square, and omega m omega square and half you may take it outside. Then you are required to get the expectation value of x square, and then the total Hamiltonian will consist of the kinetic energy term plus the potential energy term, and that will be H. that will be equal to T, expectation value of kinetic energy, plus expectation value of potential energy. But this is not the end of the story, because you have only obtained the unknown quantity A by normalizing it. Once you obtain a general expression of H in terms of B, then you argue that if we are talking about the ground state, which is the lowest lying state, the most stable state, then any variation in H with respect to B, that should give us 0. Therefore, using this argument, we determine B. Once we have this B, then from here we put it back to this place, this value of B, and try to get the minimum value for the energy of the given problem. This is how we proceed.
Excuse me, sir.
Yes.
Sir, how we will get expectation value of V? Please, can you explain?
How we will get the expectation value of V?
V. Yes, sir.
Okay. Let me. Can I change the slide?
Yes, sir.
Okay. See what I am talking about. I am talking about the wave function A is equal to AE to the power minus BX square. What is potential energy for harmonic oscillator? Half m omega square x square. Okay. What will be the expectation value of V? This will be minus infinity to plus infinity psi star x V psi x dx. This is the general definition for the expectation value of any operator. Then this will be half m omega square. Say the wave function is not normalized till date. Therefore, I am writing mod of A square minus infinity to plus infinity e to power minus bx square from this part, and from Vx part only x square, then minus Vx square dx. And that will be equal to half m omega square minus infinity to plus infinity x square minus twice Bx square dx. This will give you the expectation value of potential energy. Are you with me now?
Yes, sir. Understood.
Okay. Now what I am going to do, I am going to write a general expression, because see here, as you can see, we are supposed to evaluate the integral, and evaluating such type of integrals are not a trivial task because of the time constraint. And this will be true also in the examination, that you will be, if you such type of problems are, if they are asked in the examination, first of all, the integration either or directly for this or a standard integration is given. And what I am going to do, I am going to write, and there I will stop, the standard integration which I have found from internet. I was unable to go to the department yesterday night. Therefore, you may check it. Otherwise, I will also verify it on Mathematica. But you will check it. You may check it from internet. Minus infinity to plus infinity x power n e to the power minus ax square plus bx dx. This is equal to root pi by a e to the power b square by 4a. K is equal to 0 to n factorial n upon factorial k n minus 2k factorial 2b to the power n minus 2k upon 4a to the power n minus k. This is the integral that would be valid for any given problem. But in our case, the problem is quite simple, because we are supposed to evaluate x squared e to the power minus twice bx squared, and that means this part is 0 and n is equal to 2. Okay, your n is equal to 2. Therefore, using this, you can evaluate the value of this integral. Try to get it for this integral, and then tomorrow in the class I will come back to this. I will write the general form for the integration, and this, what I am telling you, that this will be supplied in the examination, but you must know how to use it to get any given integration. As you can also realize that if you have been given this integration formula, then any given problem that is taught to you in quantum mechanics, you can use that to obtain the solution. Okay, therefore this is a master equation, and tomorrow I will try to look for some easier, first a few easier expressions, and then I will come back to this standard integration before I start discussing harmonic variational principle. First I will use harmonic oscillator problem, and then there are a few problems given in the in this book by Griffith. I will try to solve. For example, in problem 7.1, 7.2 and 7.3 on page 298, he is talking about use a Gaussian trial wave function to find an upper limit for a linear potential, for a quadric potential, for a wave function a upon x square plus b square, and for a delta potential. We will try to obtain the solution for problem number 7.1, 7.2 and 7.3. Okay. Before that, I will try to obtain the solution for the harmonic oscillator problem. Okay, that is completely solved in the book. That is why it is useless to repeat it in the class. That is given in the Griffiths book. It is solved on page 294. You try this, and then we will try to solve the problems on page number 298, and also we will try to solve the hydrogen atom problem using variational principle. Okay, let's just stop. Thank you for today.